I'm Naomi Tague, a professor at UCSB's Bren School for Environmental Science and Management. In my research, I design computer simulation models that provide us insights into what future fire regimes may look like and how those changes are linked to other things we care about, like biodiversity and water supply. The model that I develop and apply, RESIS, integrates our best available science on how different processes work, including the processes that derive fire spread and fire severity, and the timing and of recovery of vegetation after fire, and how all of this is linked to water availability. We do our homework. We evaluate our model by comparing it with observations of stream flow, observations of vegetation growth, like tree ring widths, and observations of carbon and water fluxes. Most importantly, we compare our model estimates with observations of spatial and temporal patterns of burn probability. Once we've done this, we have a virtual laboratory that we can use to ask, what will future fire regimes look like? And how will they be associated with carbon sequestration and water supply? To give you an example, we applied our RESIS model to a watershed in the California Sierras, and we asked, what if the climate warms by 2 degrees? Or what if it warms by 4 degrees? What would happen if the 2010 drought repeated once every decade? What also would happen if we turned off fire suppression? This graph shows some of the results. This is the 10-year mean area burned. We'll notice that area burned increases once we turn off fire suppression, not surprisingly, but it is also higher for those warmer and drier scenarios. Perhaps what's more interesting is in the second and third decade, what we see is that often the warmer and drier scenarios actually have less area burned. And that's because the vegetation or the fuels are growing more slowly due to those dry conditions. We also use our model to ask questions about fuel treatment effectiveness. Right? How does the effectiveness of fuel treatment vary depending on the climate you get after you do the fuel treatment? How does it change with the type of fuel treatment or with the vegetation species or where in the watershed you do the fuel treatment? Our model then generates probability distributions that tell us how the effectiveness of fuel treatments on fire risk is likely to vary, what the implications are for carbon cycling and for water supply. Our model can also be used to say what are the most important factors that determine the effectiveness of fuel treatments for reducing fire severity risk. Is it the type of treatment method? Is it something about the particular place, like its soil depth, or is it something about the climate? What the results of our models often tell us is that things are complicated. What happens depends on the weather you get, and things about the particular location, like the subsurface, that are hard to see. So we often struggle with how do we communicate this complexity to the public? One of the things we've been doing to address that is we worked with a local artist and game designer to develop Future Mountain that takes the results from our science-based model and turns it into an interactive game that users can play. They can warm up the climate and see how this might affect the vegetation and fire in water in their particular watershed. So if you find this interesting, please visit our blog, tagueteamlab.org, or feel free to reach out to me with any questions.